Thank you very much. Thank you very much for having me, for introducing me. Today I will talk about a pedestrian model which is very specific to bus boarding situations. We already had a quite nice introductory lecture, so this takes away some pressure off me. I'm quite sure you can follow the presentation today. I'm working together with my colleague who is also in the room, Matthias Pechinger, which also mainly developed the Sumonity framework together with me, and maybe you still remember the presentation from last year. So why do we need this model? So my research is usually about studying the interaction between cyclists and buses, sometimes automated buses. And some crucial part of this scenario is, of course, passenger boarding and alighting. And so far, there is no very good model, no good integrated model in any simulation. And since we're also studying this here it's a human in the loop simulation with a bicycle simulator. Sometimes it's just pure simulation in these environments. We need to find a good solution for that. We also want to build it up on our co-simulation framework, which is we are still developing, which is called Sumonity, which uses the microscopic traffic simulations features of SUMO, but also the game engine features of 3D rendering, physics engine, and so on to have more accurate vehicle movements, and of course for this use case, high fidelity rendering. So our first step was basically, okay, how can SUMO help us in this? But we reached some limitations for that, because also we want participants to have it very accurate, to have a realistic view, to be immersed in the simulation. And for some use cases, as the use case we heard right now, I think about the Berlin network, SUMO works very good already. But for our use case, we see, okay, if pedestrians are approaching a bus stop, like they are queuing up like, let's say, little soldiers just next to each other, and also they are teleported on the vehicle onto fixed positions. So the first person goes basically on the driver's seat, the second on the place next to it, and so on, and it doesn't really consider, let's say, the geometry of the bus and where the seats really are. So we needed to find a solution to overcome that. But still, we wanted to use the SUMO as traffic simulation software, and in other scenarios, we want to use the, let's say, default SUMO models or other default SUMO models, which is also explained before. Specific use cases require specific models. So, just to give you an impression what we did. We used the Unity engine, and developed some pedestrian models and let many passengers board on the bus very fast. How this basically works is, in the bus we define certain goal points which could be imagined as the seats. We simplified it a little bit here, and then we spawn pedestrians randomly in the stop area, and they try to find a goal point on the bus, and then they move towards the bus in a certain way. And this is what I will explain right now, how this works. Compared to the models we've seen before, I think our models is a little bit simpler, and also maybe you remember my question about this interaction space, how to calculate the density and so on. This all is related to that model. Here I use a simple model which defines a certain radius of the agent, which is constant here, which could be varied of course as well, and an interaction space. If we look into literature, I use this constant interaction space now from Leo et al., which is very simple, very efficient for our use case. Usually it's elliptic, but we just made it rectangular here also to save computation time. But of course, if you look into the Nomad model, for example, which also this work is above, you should be more flexible on that. But for our simulation, with a very specific scenario, we just made the assumption that this representation of the pedestrian is sufficient. Next, of course, we had the speed-density relationship. We used some very classic literature for that, according to Weidmann. And also what we're doing is we're doing a path search. So you probably all know the A-star algorithm. You can also do this in 2D or 3D space, and that's basically what we did here. We calculate a path to our goal point, and then based on the density, we calculate the speed the person is going on that path. This then looks like that on our 3D model of the bus. This is used calling so-called navigation meshes, which divides the 3D space in convex polygons because it's the fastest for calculating the shortest path. As you can also see, it considers the agent space, so you cannot go directly to the door, for example, but you still have some distance because your body has some dimensions. And then on that blue area we can basically walk. That's all you have to know, and we're calculating the shortest path. Also, this path is basically updated every time step because as you can imagine, there are other people in the way. First, I go to the second and third point here, so about the door balancing. That's what I meant about recalculating the path. We can also detect if our path is blocked because, I don't know, we have 10 other people in front of us. So after a certain threshold, we then think, okay, let's do a rerouting to another door. If at door 1, 10 people are standing, I might go to the nearest one. Also, we encountered some deadlocks, which is just the because of the model properties we just have. Sometimes there are deadlocks that two people cannot pass each other. We can detect those deadlocks and slightly reposition one agent to resolve this deadlock. Also, which you might have seen in the video as well, we have some animations. We want to highlight that here we use just the animation for visual purposes, but there are also the possibilities that you have root motion humanoid avatars, meaning you actually incorporate the foot position or the body pose in the simulation. And if you see some videos of this animation, you sometimes see, okay, the animation is not matching completely with the speed. That's because they use non-root motion animations, because usually the correlation between the movement of the avatar and the animation speed is not linear, and you could overcome this with root motion. Okay. After knowing all this, we look at the video again. Not everything is working perfect, I guess, but you can see at some scenarios actually the door balancing in some scenarios. Here is a scenario which here it would make sense, for example, but we also see that we see some behavior which is not, I wouldn't say completely wrong, but looks on the first glance not right. Here was like this deadlock situation that we could already see. Yes, okay. We then designed the simulation study because somehow we needed to validate it. I mean, it looks okay, of course, but we needed to find some proof that it's somewhat a realistic scenario. I don't think we have the baselines that the other pedestrians models have that we've seen previously. We just want to prove, okay, it's somewhat realistic, so we can argue for realistic behavior in our simulations later. We designed our study ranging from 1 to 50 passengers, which is about the capacity of this bus. We have 4 different door configurations. So in the first scenario, all doors are completely open, and then there are some scenarios where they are half closed or only some doors are open. And we did 100 repetitions with each of the scenarios. So one scenario is, for example, 2 passengers and all 4 door configurations. So looking at the results, so this is just now descriptive results. What you see here is 2 scenarios, like basically the 2 most extreme, one with all door open and one with only one door open. Those dots in the bus are our goal points now, and the color on the heat map is basically the density that we averaged about all simulation scenarios. And I think you can see very well that, of course, for the situations in scenario 3 where only the front door is open, we have much more congestion here. We also tried, for the validation purpose, to develop or apply some regression models. Here we used a linear regression, which works well for most of the scenarios, but I again put the most extreme. We see that all doors are open. I think it's a quite good fit for scenario 3. We see that we might use some other different model as well, maybe some non-linear model. But let's look at the numbers. I think it's best you just focus on the right. The two most important numbers are, of course, the intercept and the beta value, which is basically the slope. So this beta value represents the value that if we add one more passenger, what is the additional time we have to calculate in this scenario. So for example, in the scenario all doors are open, we can just have a scenario with 10 passengers. We can expect a 0.5 higher boarding duration with 11 passengers. So that's what this says. Also, I listed some other findings. What we can see that the distribution among doors is quite important, more important even than if a door is half open or not, because we sometimes then have more openings to exit the scenario, basically, if we compare scenario 2 to scenario 4. The second point I already mentioned, the also negative intercept in scenario 3 clearly shows that we should apply another model, so not a linear model in that case. And then the most important and most interesting result to us is the last one. Since we didn't have real data for that, we had to compare it to values in literature. This is quite a challenge because many scenarios in literature are so different. So sometimes they also incorporate the time that they actually need for the seating, or sometimes it's the time when the bus departs, and this is nothing we can consider in our scenarios. So that's very different, but I think the values of the highway capacity manual are the closest that come to our scenario, and also the closest that come to a value. So they also define different scenarios, and they have a scenario with this type of bus, of course, with three open doors, and they consider, okay, for each additional passenger you should calculate 0.5 seconds, which is the exact same value which we calculated, but I think it's in the range, so we can argue what we're doing is somewhat realistic. If we do this again, or if we had more time and resources on that, what would we do? The first, I think we discussed it a lot after the last talk. I mean, heterogeneity of our crowd, of our passengers, of course, in many different ways, the agent size and so on. Also, what I want to do, because it's again about this interaction space, definitely do a sensitivity analysis on this model parameter, because of course the speed of the pedestrian highly influences the results of the boarding durations. What we also didn't include now, for reasons of simplicity and to leave the psychological factors or these tactical behaviors aside, is to consider boarding and alighting passengers. So we just focused on boarding, and the next step is to have boarding and alighting passengers at once. The next step, I will show a video to that as well, is about real-world validation. We now have the possibility to validate this, and I think the reason why I'm standing here is also to explain how we connect this to SUMO, which is quite important. This is a little advertisement of our, it's called Mobility Innovation Campus, which is a test bed which is very lately built in Munich. We can do different experiments. This is just one we built up last week actually, and it gives us the possibility to collect data. We have LiDAR sensors, camera sensors. This is something with the drone. Here we also built up a bus stop, and we also have some nice research vehicles to make some real-world tests, and this is now gaining some momentum. So I expect to collect some good data sets here soon, which we will of course share with the community. Then the last and important point, I guess, is how do we connect all of the simulation, which I basically did with the Unity game engine, to Sumo. Of course, we have this connection between Sumo and Unity, so they can talk to each other. But how do we actually do it? Of course, we have to, in real time, extract the person data, and we basically have to define two trigger events, which is person is in the waiting area and person is inside the bus. And then we can apply our simulations. And this is basically also the handshake. So as soon as the person is in the waiting area, we have a handshake between Sumo and Unity and hand over from the Sumo model to the model I just introduced. And then we can generate a waiting position, and we can generate a goal point on the bus. And then we can, then we can basically simulate what we did now. What is quite challenging still is the calculation of this navigation mesh in kind of real time, because this is kind of a heavy calculation, and we have moving objects of the bus, of course. So this is something we can do on real time, but probably now the biggest challenge to integrate it. Handing over the scenario is kind of straightforward. You just have to create good interfaces for all these different types of models. Also, we will publish this, of course, so this is now in the pipeline and will be on the public repository very soon, in a few weeks, I assume. But also for the other functionalities, we highly want to encourage you to contribute to our Sumonity project. Especially thanks to Matthias, we have now a good pipeline how to install it. It's basically just cloning the Git repo, executing one script, and then everything is running. We also have a pipeline how to test it. So if you're doing a new function, we have a testing pipeline that you're not crushing the whole system. This also works. But of course, we are also limited in resources and need you and your expertise to contribute. So if you want to work on this project, feel free to contact us or feel free to leave a GitHub issue. And looking forward to hearing from you. Thank you for your attention.